Hello students, this is Dr. Siva Nagaraju from IARE. Today we are going to discuss problems on analog pulse modulations. Previously we discussed the theory according to this analog pulse modulation. Now we are going to solve some numerical problems on this analog pulse modulation. So before going to analog pulse, we know that sampling is must and should. So we are going to sample. So today problems are on sampling. Okay. And in analog pulse modulation, pulse amplitude modulation is the first one. So some problems are on pulse amplitude modulation also. Okay. So this topic come under module 3, and module 3 is covered by course outcome 3. So what the course outcome 3 says? Illustrate the concept of pulse modulation schemes, demodulation, sampling, quantization, and coding for obtaining of digital data. So why? Because this course is analog and digital communications. So in analog digital communications, we are going to cover from modulation, and again in modulation, what is analog and what is digital and how to convert digital. So these are all discussed in this course. So that's why the course outcome 3, which is going to illustrate the concept of pulse modulation. So today problems are pulse modulation schemes. Okay. So now the first problem. Specify the Nyquist rate and Nyquist interval for each of the following signals. So we are going to sampling. We are going to follow the Nyquist criteria. So that's why today problems are on Nyquist rate and Nyquist intervals. So there is nothing but sampling. Okay. So in this problem, we're having 3 parts. The first part is g of t, which is equal to sinc of 200 t, sinc pulse. So here we know that how to write the sinc pulse. Okay. So for taking the first one, g of t is equal to sinc of 200 of t, that we can write sine of 200 pi t divided by 200 pi t. So this is the sinc pulse actual. So in the short form we can write sinc of 200 t, but actual it is the form of sine of 200 pi t divided by 200 pi t. So here the frequency component you can represent by using a W or FM, whatever maybe. Okay, is 100 hertz. So the Nyquist rate, you know that Fs is equal to Fs greater than equal to 2 FM. So here you can write the Nyquist rate. Nyquist rate, that is simply you can say Fs is equal to or greater than equal to 2 FM. So this is FM. So our Nyquist rate is nothing but 200 hertz. Simply 2W. No problem. You can use FM or W. So finally the Nyquist rate is 200 hertz. And the Nyquist interval. So simply it is you are going to divide or reciprocal you can take. So there is 1 by Fs Nyquist interval is equal to 1 by Nyquist rate. So 1 by 200, simply it is 5 milliseconds. So this is the solution for the first part. Why? Because this problem is containing 3 parts. So the first part is g of t is equal to sinc of 200 of t. We are going to find the Nyquist rate and Nyquist interval. Okay. So coming to the second one. So this one is a sinc square. Simply the second problem is a sinc square 200t. Sinc square. So the highest frequency component of g of t is a sinc square 200 of t, 200t. So it is twice of that first one. The first part is sinc of 200t, but is a sinc square. That means we are going to multiply 2 sinc pulses, getting the sinc square. Okay. So we are going to squaring the bandwidth signal as if the doubling its highest frequency component. So g of t we can write as a sinc square 2w t. Sinc square 2w t. So 2w. So 2 into 200. So the Nyquist rate, the rate is 400, and Nyquist interval is equal to 1 by 400. It is equal to 2.5 millisecond. 2.5 millisecond. So this is the second part. And third one. So third one is the addition of the first one and the second part. You can say g of t is equal to sinc of 200t plus sinc square 200t. Okay. So you can say the first one is sinc of 200t and second one is sinc square of 200t. So for this problem, you can consider the highest frequency component of the composite signal. So this third one is the composite signal. One is the normal sinc pulse and another is the square of the sinc pulse. We are going to adding these two pulses. You can call it as the composite signal. So in this composite signal, we are considering the highest frequency component. So the highest frequency component is again here nothing but this rate is 400 hertz. 400 hertz 2w of t. So here you consider for this third one, the Nyquist rate is similar to 400 hertz, and interval Nyquist interval is also similar to the 2.5 milliseconds. Okay, for any compound signal, we are considering the highest frequency component of the composite signal. Okay, so this is the way to solve. Now coming to the second one, find the Nyquist rate and the Nyquist interval for each of the following signals. So here given 3 problems. One is a m of t is equal to 5 cos 1000 pi t into cos of 4000 pi t. One bit, and the second one is m of t is equal to sin of 200 pi t divided by pi t. And third one is sin of 200 pi of t divided by pi t square. Okay. So here also you consider the highest frequency component for the third one. So just similar to the first problem. Okay. So first to considering the a bit. So what the a bit says? M of t is equal to 5 cos 1000 pi t plus cos of 4000 pi t. Okay. So my m of t is equal to 5 cos 1000 pi t into cos of 4000 pi t. So here we are taking as cos of a plus b and cos of a minus b. You can consider the problem formula, trigonometric formula. It is in the form of cos a cos b. Okay. So for the rearrangement of this, 2.55 of cos of 3000 pi t plus cos of 5000 pi t. Why? Because it is a form of cos A cos B. So here we are going to write the form of cos of A plus B plus cos of A minus B. So here you can see A plus B and A minus B. So it is 2 cos A cos B. So here you are getting the by 2. So 5 by 2 is 2.5. Okay. So here in this signal, you can consider this a composite signal. The maximum frequency component we taken as a 5000 is 5000. Why? Because this is in the form of 2 pi. So FM is nothing but 2500. Okay, for the composite signal, we consider this one is 2500. That is FM. And the Nyquist rate, Fs is simply taken as greater than or equal to 2 FM. So Fs is nothing but 5000. And again the Nyquist interval. The interval is equal to 1 by Fs, that is equal to 1 by 5000. We are considered as 0.2 millisecond. Okay, so this is the way. So this is the first problem, a bit. Now we go for the second problem. So coming to the second problem, it indicates in the form of sync pulse. So that is sine AT divided by pi t, which is equal to this function p of a, which is equal to 1, 0 for omega less than equal to a, and omega greater than equal to a, it is 0. So for the band limited signal, we are taking FM. So for this FM is nothing but 100, and Fs is nothing but 2 FM, so 200. And similarly, the interval is 1 by Fs, that is equal to 1 by 200. So it gives some 0.5 seconds. Okay. So this is my interval. Or simply you can stop here to 1 by 200 seconds. For coming to the third one, so here is the square of the previous problem. So we are taking the highest frequency component is 200. So here my FM is changed as 200, and Fs is equal to 2 FM. So it is 400, and the interval is nothing but 1 by Fs, that is equal to 1 by 400 seconds. So this is the Nyquist interval. Okay. Very big problem. So here in this problem, it contains 4 bits. A continuous time signal is given by x of t, which is equal to 8 cos 200 pi of t, 200 pi t. Determine minimum sampling rate, that is Nyquist rate, required to avoid aliasing. Second bit is if sampling frequency Fs is 400 Hz. What is the discrete time signal? x of n or x of nts obtained after sampling if sampling frequency is 150. So here the first problem, here the problem is showing a very big one, but not to worry, it is very simple one. So here we're going to find the first one is Nyquist rate, and second one is the change in the sampling frequency on Nyquist rate is 400 is for one time and 150 hertz for the second time. Okay, and the last one is what is the sampling frequency? The frequency is in between 0 to fs by 2 of the sampling rate of sinusoidal that yields the samples identical to those obtained in part 3. Okay, so in part 3 we are concerning. So in part 3. Okay, so here we are taking the highest frequency component of the continuous time signal. So f is equal to 100 hertz. So f is 100 hertz. So once again you can see here, you can see x of t is equal to 8 cos 200 pi t. Okay, so here the fm is nothing but 100. So f is simply 100. So the minimum sampling rate is required to avoid the aliasing effect. Avoiding the aliasing effect is called the Nyquist rate. So simply the Nyquist rate is equal to 2f. So that is equal to 2 into 100, 200 hertz. So already we solved in the previous one, similar. Okay, and this is the first part. The second part, why? Because here taken as 4 parts. So the second part, here the sampling frequency they given as 400 hertz. Fs is 400 hertz. So here we are going to convert this continuous time signal into the discrete one. So what you do when you convert any continuous signal to discrete time signal, we must go for the sampling. Okay, so here the frequency of the discrete time signal will be f is equal to frequency of continuous time signal divided by sampling frequency. So what is the continuous time signal? That is 100. Already we can see. Now my sampling frequency is 400. Now it is 1 by 4. So f is 1 by 4. So how can you write x of t into x of n? X of t is the continuous, x of n is the discrete one. So x of n you can write 8 cos 2 pi f into n. Okay, so 8 cos 2 pi f is 1 by 4 into n. So finally my x of n is equal to, so here 2 times, that is 8 cos pi n by 2. So this is the discrete one. For a given sampling frequency 400 hertz, we got the discrete time signal is 8 cos pi n by 2. Okay, and for the third one, here the sampling frequency is 150 hertz. Same procedure. So for the third one, simply this 400 hertz is changed as 150. So here you can write 150. So what you got? Simply you got 2 by 3. 5 2s, 5 3s. Okay, 2 by 3. Now here you can substitute in the place of f. Sorry, here same. So here you can substitute 2 by 3. So here also same. So here a denominator is not going to cancel the numerator 1. So it is 4 pi n by 3. Okay, simply 4 pi n by 3. So this one, same problem. Just they change the sampling frequency. So we are going to substitute in the place of 400 as 150. Then you got the frequency is f equal to f, not frequency. F equal to 2 by 3. So we go to substitute the f value here. Then you get the discrete one. Okay. Coming to the fourth one. So the fourth one is a continuation of the third one. So here the Fs is 150 hertz. Fs equal to 150 hertz. Then capital F is equal to F by Fs. Or we can write small f is equal to capital F into Fs. So here Fs value is 150 and the given 1 by 3. Okay, so here you use 150 into 1 by 3, then it is 50 hertz. What is 50 hertz? Small f. So the continuous time signal would be 8 cos 2 pi ft. So t indicates continuous time. Why? Because so this is a continuous time signal. So this is my t. Here I am going to samples like this. Then it is in discrete form. So now in this way it is going to samples. If amplitude also samples, then it is called quantization. If time is going to samples, it is can be called as sampling. Okay. So 8 cos 2 pi f is 50 into t. So simply 8 cos 100 pi t. This is my continuous time signal. So this is the continuation of the third problem. Okay. Third part. Now we go for the another problem. So here determine the Nyquist rate for a continuous time signal. X of t is equal to 6 cos 50 pi t plus 20 sine 300 pi t minus 10 cos 100 pi t. Okay. So this is also a composite signal. You can say continuous time signal. So x of t is equal to a1 cos omega 1 t plus a2 cos omega 2 t plus a3 cos omega 3 t. So this is in the form of this equation. The given equation is in the form of mathematical. Okay. So x of t is equal to 6 cos 50 pi t. So here you go to compare the given one with the reference one. Okay. So comparing f1 is equal to omega 1 by 2 pi. So here omega 1 is 50 pi divided by 2 pi. It is 25 hertz for the first part. And second one, f2 is equal to omega 2 by 2 pi. So 300 pi divided by 2 pi. So you got 150 hertz. For f3, we use omega 3 divided by 2 pi, that is equal to 100 pi divided by 2 pi. So 50 hertz we got. So for any composite signal, we are taking the highest frequency component. Out of these three frequencies, which one is the highest? 150 hertz is the highest one. Okay. So for this, F max is 150 hertz. So I am considering this one. Okay. So the Nyquist rate. The Nyquist rate is Fs greater than equal to 2 Fm. So here what you got? 2 into 150 hertz. So finally this is 300 hertz. Okay. So in this problem they ask only Nyquist rate, not equal to the Nyquist interval. For the Nyquist interval, simply equal to 1 by 300. That is the Nyquist interval. But in this problem they didn't ask. Okay. Coming to the next problem. Yeah. This problem is belongs to the pulse-amplitude modulation. Why? Because PAM is the first pulse modulation scheme. Okay. What the problem is asking? For a pulse amplitude modulated transmission of voice signal having a maximum frequency equal to FM is 3 kHz. Calculate the transmission bandwidth. It is given that the sampling frequency Fs is 8 kHz and the pulse duration tau is equal to 0.1 ds. Okay, they given FM, they given Fs. Okay, so what they ask? Calculate the transmission bandwidth. Okay, so first we go to find the Ts. Here they given 0.1 Ts. So first, what is a Ts? So sampling time. How do you find the sampling time? Just from the reciprocal of the sampling frequency. So 1 by Fs. So what is my Fs? 1 by 8 kilo. 1 by 8 kilo. So that is 1 by 8 into 10 cube. So if this 10 cube come to the numerator, it is milliseconds. 1 by 8 is nothing but 0.125 millisecond. So this is my sampling time. So what is the pulse duration? Tau is equal to 0.1 Ts. So 0.1 into 0.125 millisecond. So here you can multiply, then the pulse duration is 12.5 microsecond. You can convert it into microsecond. So you find the pulse duration. Okay. And then we go for the transmission bandwidth. So what is the bandwidth? Which is greater than equal to 1 by 2 tau. So tau is 0.1 Ts. So you find the tau value. Now you go to substitute 1 by 2 into 12.5 micro. So micro means 10 power minus 6. So simply send this 10 power minus 6 to the numerator. It is going to 10 power 6. So 10 power 6 divided by 2 into 12.5. Simply it is 25. So my bandwidth is 40 kilohertz. 40 kilohertz. Okay. So this is the way to solve the problem. for bandwidth. Okay. Next, 61. The spectrum of bandpass signal Z of t has a bandwidth of 0.6 kHz centered around plus or minus 12 kHz. Find the Nyquist rate for quadrature sampling of in-phase and quadrature components of the signal Z of t. So they are asking here in-phase and quadrature components. Okay. So G of t, you can write G I of t cos 2 pi fct minus Z q of t sin 2 pi fct. So for G of t bandpass signal contains both the in-phase and quadrature components. Okay. So G I of t into cos of 2 pi fc. So here the fc is given as a plus or minus 12 kilo. So taken as positive 1, this one, minus gq of t sine of 2 pi fc. Here also 12 q t. So where G I of t and Z q of t are low pass signals with a bandwidth of W is equal to 1 by 2 into 0.6. So 0.3 kilohertz. So this is the bandwidth. Okay. Given signal bandwidth is 0.3 kilohertz. So the Nyquist rate, here they ask find the Nyquist rate. So the Nyquist rate for the in-phase and quadrature component is therefore Fs is equal to 2W. So what is my W? 0.3. So 2 into 0.3 gives 0.6 kilohertz. So this is the sampling frequency or Nyquist rate. Okay. Coming to the next one. Yes. Find the Nyquist rate and the Nyquist interval for the given signal. X of t is equal to 1 by 2 pi cos of 4000 pi t into cos of 1000 pi t. So it is similar to cos A, cos B. So you can use your cos of A plus B plus cos of A minus B formula for solving this one. Okay. So X of t is equal to 1 by 4 pi of cos of 5000 pi t plus cos of 3000 pi t. Why? It is in the form of 2 cos A cos B is equal to cos of A plus B plus cos of A minus B. So in this formula, trigonometric formula, I am going to substitute cos of A plus B. 4000 plus 1000, 5000. 4000 minus 1000 gives 3000. Okay. So here two frequency components are there. One is omega 1 of t. It is 5000 pi t. So it's not omega 1 of t, omega 1 t. Okay, omega 1 t. So what is omega 1 angular frequency is equal to 2 pi f and t 5000 pi t. Though this t cancel, this pi cancel. So f1 is equal to 2500. This is one. Similarly, the second one, omega 2 of t, that is equal to 3000 pi t. And what is f2? 2 pi f2t is equal to 3000 pi t. So again tt cancel and this pi term cancel. So f2 is equal to 1500. f2 is 1500. So what they ask? Nyquist rate. So what is the formula? Fs greater than equal to fm. So here two message signals are there. So which one are you going to choose? Similarly, the maximum one. Already you know that the maximum one you go to choose simply. So that is equal to 2 into 2500. Then it is 5000 Hz. So this is the Nyquist rate or sampling frequency. And the Nyquist interval Ts is equal to 1 by Fs, that is nothing but 1 by 5000 Hz. Then it is 0.2 millisecond. So this is the way to solve this one. Okay. And coming to the another problem. Yeah. This one. Two signals x1 of t and x2 of t are sampled with a sample frequency of 40 Hz. Obtain the associated time signals x1 of n and x2 of n. That means after sampling, it is in discrete form. Okay. So why are you using sampling? We are going to convert the continuous time signal into discrete one. Why? Because this is the first operation for convert continuous time into digital signal. Okay. That means continuous, discrete, then digital. In analog pulse, we are going to discrete in time only, not in amplitude. If you go to discrete both in time and amplitude, then it is the full discrete form. For the pure discrete form signal, you are going to apply coding, then it is converted into digital one. Okay. So in analog pulse, we are doing only half. What is the half? You are going to discrete in time only, not in amplitude. So that's why it is analog pulse. So in analog pulse schemes, you are having pulse amplitude, pulse width, and pulse positions are there. Whereas in discrete, you are having in digital, you are having a PCM, DEM, DPCM, ADM, like that. Okay. So taking the first one. x1 of t is equal to cos 20 pi t. 20 pi t. So here again we taken as omega 1 is equal to 20 pi t, omega 1 t. Okay. So omega 1 t is equal to 20 pi t. So 2 pi f1 of t is equal to 20 pi t. So tt pi is going to cancel. F1 is equal to 10 for the first one. Again the second one, x2 of t is equal to cos 100 pi t. Okay. So again here also omega 2t is equal to 100 pi t. So it is nothing but 2 pi f2t 100 pi t. So this tt, this pi term is going to cancel. Then f2 is equal to 50 Hz. Okay. So this is two signals, but we are going to convert these two signals into the discrete one. Okay. So x1 is obtained by replacing the time equation by n by fs. Okay. N by fs. While here the sampling frequency is given as 40. So simply 10 by 40 we can substitute. Already done. Okay. So x1 of n is equal to cos 2 pi f1 into n by fs. Okay. So cos 2 pi f1 10 into n divided by fs is given as 40. So this 40. So you got these two also cancel. Cos pi n by 2. So this is my x1 of n. Whereas x2 of n. x2 of n is equal to cos 2 pi f2 into n by fs. Same frequency you could take it. Okay. So here also you got to substitute. So cos 2 pi f2 50 into n divided by 40 and this is 2. So simply cos of 5 pi n divided by 2 x2 of n. Okay. So this one. So this is how to convert the continuous time signal into discrete one. Okay. And this one, the last one. An analog signal is given as follows. X of t is equal to 3 cos 50 pi t plus 10 sin 300 pi t minus cos 100 pi t. Find the Nyquist rate. So this is a compound signal. You can consider individual and find the highest signal. Then you use this highest signal as the Nyquist rate to convert the Nyquist rate. Okay. So from this here you can consider f1 is equal to, here first one is 25 and f2 is 150 and f3 is 50. Already we saw the number of, so I here taken directly. Okay. So f1 is 25 Hz and f2 is 150 Hz, f3 is 50 Hz. So out of these three, which one is highest? Is 52. f2 is equal to 150 Hz. So this one, f2 is 150 Hz. So this is the highest one. So I am considering the highest frequency component. Okay. f is equal to fm. So what is my highest frequency component? F max 150. So 2 into 150. So that is 300 Hz fs. So this is the Nyquist rate is 300 Hz. Okay. Okay. Thank you. So here the references are taken from Simon Hacking, Thornton, and also from Sanjay Sharma. Okay. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.